Thanks for joining us today. On behalf of VMware, I would like to welcome you all to this evening. And I'm Sabri. Can you go to the next one? I'm Sabri. I work in the VMware Integrated OpenStack team here at VMware. And in the past, I've been associated with OpenStack for quite some time. And this is going to be a short talk, and it'll probably get over before you finish your drinks. Let's get started. Let's cut to the chase and get started. So I'm going to talk about why you should run Kubernetes on OpenStack. Can you go to the next slide? Yeah. So why would you choose OpenStack to run your Kubernetes distribution? In OpenStack, you have everything that you need to run your production-grade Kubernetes cluster. So I'll give you 3 reasons. Let's start with reason number 1, the ease of deployment. So there are tons of options available out there to deploy Kubernetes on OpenStack. You could choose some of the native services in OpenStack like Magnum or Murano, or you could build your own custom solution using certain tools that I mentioned over there. Or if you're really interested in an enterprise-ready Kubernetes distribution and you want it to be like a turnkey solution, you could as well use our recently released VMware Integrated OpenStack with Kubernetes. So these are your options. It's really easy to get going on OpenStack with respect to Kubernetes. Reason number 2, if you're looking to deploy a production-grade Kubernetes cluster, chances are high that you really want it to be like highly available. That is, you basically put a load balancer in front of it, and you want it to be like really scalable. With OpenStack, you could leverage features such as Neutron LBAS, or you could leverage Autoscaling to set up such a really great architecture. And actually, I think I made a terrible mistake over there. I have an enterprise logo, and I just quoted Yoda before, so if I offended anybody, sorry about that. And the reason number 3 to deploy Kubernetes on OpenStack is, this is quite the important one, and that's what we'll be dwelling into today, is the cloud provider interface. So what is a cloud provider interface? So basically, if you deploy a Kubernetes cluster with a cloud provider interface, there are certain advantages that you get. The idea over here is that you're not only leveraging the underlying cloud for its capacity, but you are also leveraging certain features such as load balancers and persistent volumes for your container workloads. So this is like your container workloads are now directly interacting with the underlying IaaS to enhance its capabilities. That's the richness that you get when you deploy Kubernetes on OpenStack. And for this to work, you need to have the cloud provider interface implemented for your specific cloud. So out of box in Kubernetes, this is implemented for OpenStack, and it just works. So we have tried it on day 1, it just works. So it's really production ready. The cloud provider interface is awesome. And let's dwell deeper into why do you need it and what are the other advantages of this cloud provider interface. So what's the big deal with the cloud providers, right? So that's what we are going to talk about in the next few slides. The first one, I would say, is the external load balancers. Say you have an application deployment that needs, can you go to the next slide? Thanks. Say you have an application deployment that, for example, consists of, API gateways or things like that as part of it. You would probably want it to be exposed to the outside world, right? So for this to happen, your Kubernetes services could just request for an external load balancer, and the cloud provider will work in conjunction with the IaaS underlying, which is OpenStack in this case, and create a load balancer for you and route the traffic to your specific nodes. I can explain this quickly. So let's start with a couple of nodes in your deployment, and let's schedule some pods on them. Can you go click on that? Yeah, thanks. So you could schedule some pods on it. And the next thing that you would do in Kubernetes is like create a Kubernetes service. So a Kubernetes service basically is a logical entity which redirects traffics that are onto specific pods matching a specific label. So in this case, if you create a Kubernetes service, can you go to the next one? I'm really sorry. I should have asked for a presenter remote. I don't have it, so it's kind of getting awkward. Yeah. So when you create a Kubernetes service, the traffic is basically routed to the specific pods on specific ports. But this will only happen within the cluster network, or you could use a concept called node port, and you could redirect traffic that are arriving at the nodes to specific pods. But what if you want your external traffic to reach your pods? So what could happen is that your Kubernetes service could now request for a load balancer by specifying a type load balancer in the service spec. And what happens is that when you create this resource, the cloud provider in Kubernetes will talk to the underlying IaaS to create a load balancer. So in this case, with OpenStack, it's going to be a Neutron LBAS load balancer. It's going to be the next one. So it's going to be dynamically created, and it will route traffic to the specific Kubernetes service. So this is really awesome, because now you have your pods, and the traffic to the pods are now getting redirected from an external network. And all this is happening because the container platform is able to talk to the underlying IaaS platform to provision this. The next biggest advantage is persistent volumes, which is the next slide. So with persistent volumes, say you have some stateful labs as part of your deployment, right? And they need persistent storage. So with the cloud provider implementation, what happens is that it can talk to OpenStack Cinder service to create a pod, and then, to create a volume and attach it to one of the Nova nodes, which is running your Kubernetes services. So that's what exactly happens. And Kubernetes will take care of mounting the specific Cinder volume onto the pod. So this is all taken care by Kubernetes. So what happens if your specific node dies, right? So for example, your node dies, and what Kubernetes would do is make sure the pod comes alive on a different node. This is just like how Jon Snow got back on Game of Thrones, if any Game of Thrones fans are here. So if your node dies, the pod is just brought back on a different node, and the magic here is that the Cinder volume gets moved as part of this to the new node as well. So all this is taken care of by the cloud provider implementation as part of Kubernetes for OpenStack. So we looked at that, and these are some of the highlights of it. But there are also some few other awesome things that you could do with this specific stack, is that you could basically, the next one, you could basically leverage Keystone for your authentication purposes. So if you have set up Keystone once with LDAP or whatever backend it is, you could basically use the same for your authentication for your Kubernetes cluster as well. So you don't need to go hunt for a different IDM. Keystone is the best in class IDM for your Kubernetes plus OpenStack together. And you could also run like custom authorization plugins on Keystone, so that you could leverage the projects and users concept in Keystone. You could map them back to your Kubernetes cluster. And the last thing is that when your node is automatically deleted, your node is deleted on OpenStack, it gets deleted on Kubernetes as well. So you don't really have to clean up anything on Kubernetes side. It's all like dynamic. So when you scale up and scale down, nodes get added, joined to the Kubernetes cluster, and when they are deleted, they just leave the Kubernetes cluster. So these are some of the things that was only possible because of the cloud provider interface implementation in Kubernetes. And as always, there are some things to watch out for. If you're going to go for this solution, then you need to make sure that since each worker node is now making OpenStack API calls, you want to make sure that it really scales well. That is, your underlying OpenStack cloud is like really scalable as well, because as you deploy more and more Kubernetes services, they're going to make Neutron API calls. As you're going to create more Cinder volumes, it's going to make Cinder API calls. And last but not least, you need to make sure the quotas for each projects are increased wherever you deploy the Kubernetes cluster. And thanks for coming here. Kubernetes and OpenStack is a powerful combination for your application container workloads. Thank you. Thanks a lot.
Thank you, Lisa Marie and the Bay Area OpenStack group for having me. She's not kidding. I think she's been chasing me for about a year to do this, and I didn't think I was going to do it. I've flown 175,000 miles this year, and I thought I was done for the year. And then I ran into Lisa Marie in the airport in Sydney, and she said, you got to do this. So yeah, she was stalking me all the way to Sydney. But I'm so glad to be here. I've been meaning to do this for quite some time. Thank you to Elsa and VMware Code for hosting us, and the AV team for putting this together. and to Sab for warming us up with Kubernetes on OpenStack, which is very topical and right in the heart of what we're going to talk about here today. So if you want to talk about Kubernetes or Docker, there's this sort of unspoken rule. You have to have all these nautical references, right? So I'm just going to lay them on thick, right? We are going to sail with the trade winds. So if you know anything about sailing, and I know nothing about sailing, but this map kind of tells you a lot about sailing, which is there's these prevailing winds that take you in certain directions. And in fact, that's more or less how the Europeans found North America and South America. For thousands of years, no one had the wherewithal to cross the ocean long after we knew the world was round, mainly because they were sailing too far north. And too far north, if you're sailing from Europe, you're just sailing against the wind, and that doesn't work very well. Well, eventually, Columbus and others figured out if they sailed a little further south, they'd catch a tailwind all the way to the Americas. And on the way back, they'd have to sail up a little bit further north. That's all about reducing friction, and that's the way that that works. So we're going to draw some of those analogies to development. You know, what I think we're here to talk about, technology. Basically, if you sail with the wind to your back, things go a whole lot smoother. And as developers and engineers, that helps us get our job done a lot quicker and a lot easier. So we've got a couple of things we're going to talk about here. First and foremost, we're going to hit a few high-level concepts, just make sure we lay a groundwork. Those high-level concepts, though, won't really dive directly into the technologies. Then we'll talk about the technologies. And then finally, I've got a handful of case studies, places where the technology and the concepts that I'm talking about previously are being used. And all of it will have, as you can imagine, a little bit of an Ubuntu flavor to it. Maybe more than a little bit, but some. Okay. So we'll start with the concepts. And I'm sure you've heard of these, right? 12-factor. Who's heard of 12-factor? Yeah? Can you name all 12 factors? Can you name one factor? No, not even one? Oh, come on. Somebody give me one factor. There you go. Logging data streams. That's great. I won't challenge you for any more. If he knows one, he probably knows all 12. Cloud native. Who knows what cloud native is? Boy, it sounds good, doesn't it, right? Cloud native foundation, cloud native computing. It's a group of concepts. Containerization, right? Everybody wants to containerize. Containerize your apps, containerize your infrastructure, containerize containers. We're going to take containers and put them in containers. We're going to take OpenStack and put it in containers. We're going to take containers and put it in OpenStack. So containerization, right? Lots and lots of containerization. We could go through all 12 factors. I've memorized them once. I've forgotten them more than once. We could really put a definition to cloud native. I'm going to give you the 5 things that I think are important here. And the 5 things that I believe are at the heart of all of this, maybe some of these you could break down or put them together. This is the first one, and we've known this for a long, long time. I've been around open source for almost 20 years, and one of the early tenets of anything you ever did with Linux and open source was what? Release early, release often, right? That's part of Agile, it's part of open source. Ship early, ship often is sort of the modern approach to that when what you're talking about are web applications, ultimately. More so than, say, an open source project, you know, of which I maintain a few. That's different than your large-scale web application or working on a team developing a web application. The first tenet, I would say, to that 12-factory cloud-native containerized world is this. And it really starts with this. Shipping early, shipping often, iterating, and being able to fall back gracefully. And that's one of the important points, is that when you try something and it doesn't work, you roll it back. Especially when you're talking about deploying this to millions of users, right? You got to have canaries out there. You deploy it to 1/10% of your users and see who screams. And if someone screams or a cat dies, well, unless you're trying to kill cats, you probably want to back out that change, right? So this is the first one, all right? And that's a concept. We're not talking about a technology, we're talking about a concept. And I didn't even try to, but there's even a nautical reference in there. I promise that wasn't even intended. I noticed it after the fact. This is another one that I think you'll find codified in cloud-native methodologies, but rarely stated quite as such. But I think this one's super important and at the heart of why we talk about containers. And at the heart of why containerized applications, the cloud-native applications work really well. Optimizing resources, right? Who here has a data center accessible to them? I mean, surely at work, right? You've got physical hardware, you've got public cloud or whatever. Prior to the concept of cloud computing, we had a lot of idle hardware, right? Most hardware was actually idle in many organizations. Since we've moved a lot of that to the public cloud, that gets optimized and used a lot more efficiently. Since private clouds or private infrastructure has moved to OpenStack and private clouds, resources are shared far more efficiently, right? Containers takes that to another level by deduplicating the number of Linux kernels that you have to run on a system to do anything, right? You can run a single Linux kernel with thousands of containers as opposed to a single Linux kernel running dozens or maybe hundreds in a really dense case of copies of the Linux kernel to run more applications, right? That's one way of optimizing those resources. Think about GPUs, you know, especially the sort of the revolution around software that we're really at the very earliest stages, just the tip of the iceberg of how transformative GPU technology will be in our industry. And just wrap your head around that for a little bit. The next 10 years will be defined by artificial intelligence. And it's kind of ironic that, you know, I was in college in the 90s and we were talking about AI. And I don't know, it was academic, but sort of fizzled out and never really became part of our daily lexicon, right? We're at the stage right now today where you were hearing about, you know, containers for the first time, or maybe VMs or the cloud the first time a decade ago, or virtual machines even further before that with VMware. If you were talking about virtual machines in the 90s, you were probably talking about an IBM mainframe. That's where we're at today with AI, and it is driven by containers and GPUs, and I'll link back to that in a few minutes, okay? But optimizing resources is the second piece of really being a cloud-native developer, or accelerating the velocity of developers. The third one is autoscaling, right? So optimizing the resources that you have is important, certainly important to your ops team and your system administrators. But if you're writing your application, you want your application to not fall over. It needs to auto-scale. It's important that it scales up, but it's also important that it scales down, right? That compression expansion is quite natural and important to the previous point of optimizing those resources, right? It's no good if your infrastructure scales up, but it doesn't vacuum out those resources. You'll end up overpaying Amazon or your cloud provider if you're not auto scaling. The modern application is written expecting this. Or if you're a developer and you're writing a modern web application, you should be able to expect this from your underlying infrastructure. If not, you should really be rethinking what infrastructure you're dealing with, because it's not accelerating your velocity, okay? So auto-scaling is number 3. The fourth one, which is part of auto-scaling, but it's not exactly the same thing, but self-healing infrastructure. Something goes wrong, inevitably, all the time, no matter what. You can test your software all you want. Test your provider, your network, your storage all you want, and the unexpected happens, right? You've had an unexpected data loss. The thing that you least expected to break, broke, right? The thing that you least expected to go down, went down. The person that you depended on to maybe push the button left for one reason or another. We used to say got hit by the bus, now we say they won the lottery, right? They left, they're not here anymore. That cannot happen in a modern application. Modern applications themselves should be aware, but they also should have an infrastructure underneath it that's able to handle healing of common problems and constantly getting better. That's the important point, is that, sure, we're going to hit the unexpected. We always hit the unexpected. Go ask Netflix. They hit the unexpected all the time, and you'd think they've solved every problem that you could have at 100,000 instance, one of the world's biggest and most famous applications, right? But when they do hit the unexpected, there's an outage, and that's unfortunate. It makes the news and impacts the stock price, but I guarantee you that problem doesn't happen a second time, right? That infrastructure is then codified to avoid that through a self-healing mechanism. Okay, still not talking about technology. We're still on the high-level concepts, right? And so finally, the last one is a bit of a controversial one, but think through what fully managed means, right? In some cases, fully managed means there's a consulting company out there wanting to sell you services around managing infrastructure, and that's fine, and there is that, and we sell that, and our competitors sell that, and others sell that. But think about what fully managed really means. It means that fundamentally running that service is someone else's problem. Maybe it's an outside vendor. Maybe in a big organization, it's another part of the organization. But someone's taking care of caring and feeding for the hardware, the software, the other resources that are necessary here, right? Disks fail, they inevitably fail. Someone's got to go into that rack, yank that disk, and put it back in a fully managed infrastructure below the part of the stack that the application developer cares about. That there's a certain amount of management that is expected. And outside of a startup, and I've been part of 10-person startups before, where everyone has to do a little bit of everything. Once you graduate beyond that, there's quite a bit of expertise that you come to depend on that's compartmentalized, and compartmentalized for efficiency reasons. And this factors into fully managed. So I'll just review those right quick to make sure that, I see some people are taking notes. What we had here, ship early, ship often, optimizing resources, auto-scaling, self-healing, and fully managed, okay? Those are the high-level concepts, and I appreciate you sticking with me through this. And by the way, I love that people are taking notes. That's awesome. I think part of it is, who has the Wi-Fi working? Does anybody have the Wi-Fi working?
Fine.
Ha-ha, I love it. Elsa, that's the best part of all of this. There's no Wi-Fi working, and all the attention is directly right here. That's the happiest accident of the night. Okay, so now let's dive into technologies, right? What? Oh, your thumbs down? No, come on. Come on, Twitter can wait. Twitter can wait. Let's dive into some of the technologies, right? Hopefully that intro was a little bit helpful to dive into some of the technologies. So, you can't swing a cat without talking about Docker, right? So we'll talk about Docker. We do a lot of work in Canonical and within the Ubuntu ecosystem around Docker. And I'm happy to say that we love Docker, and Docker users seem to love Ubuntu. That happens at a couple of different levels. We work closely with the Docker team to ensure that Ubuntu and Docker are well tested together, that we've always got latest and greatest Docker binaries, both the Community Edition and the Enterprise Edition, available on Ubuntu. That's a relationship that goes from the community and development level into the commercial and enterprise level. And with that integration, we see a one type of container technology that's super well integrated with Ubuntu itself. We also do quite a bit of work to ensure that the Ubuntu images inside of Docker Hub are well cared for, well curated, that CVEs are patched there frequently on a regular cadence. We do that on a regular cadence of about every 3 weeks. And then we can, anytime we need to, we can push an update ad hoc if there's something that's super critical. So users can come to expect, users of the Ubuntu image in Docker Hub, meaning if you've got a Docker file whose first line is from Ubuntu, and then that image is coming from Canonical. It's tested by the Canonical Foundations team, which builds Ubuntu and makes that same image available in all of the public clouds in the world, and that it's well tested, well integrated. So that's Docker as a host. We make sure that the Docker binaries are well tested in Ubuntu, that the kernel is optimized for container workloads, and there's a lot of container workloads, but specifically Docker workloads especially. And the Ubuntu image in Docker Hub is well curated. And that happens in partnership with Docker Inc., which is important to us. It's a technology, but it's also a company that we work closely with. So Docker is one type of container. It's not the only type of container out there, but it's one type of container, and it is the type of container that I think people came to know that really brought containers into the front part of our brains, I believe. Containers have been around for a long time. I'm sure you've heard this now as the history of containers is well detailed. There's a lot of different types of containers. We talk about Docker containers as being process containers. A Docker container contains one application, one process per container, okay? There's a different type of container that we also do a lot of work on in Ubuntu called LXD containers. LXD containers are machine containers, whereas a Docker container typically has one binary or one process running in that container. And if you want to run a different binary, you should launch a different container and then make those talk to one another. LXD is actually a machine replacement. So inside of a LXD container, you have more than one process. In fact, the first process is systemd. That container boots. It goes through a very small, very quick boot process that skips all the kernel bits, but it launches a handful of other user space processes. So off of PID1, systemd, you'll get a cron daemon. You'll get an SSH daemon. You'll get a TTY and a journal. And that's about it. It's only about a dozen or so processes, but it's just enough that if you logged into that machine, it is a machine, it would look like a machine. The kernel is shared with the host, but otherwise you treat it just like a machine. It draws an IP address using DHCP. By the way, DHCPD is running. It's either bridged to the network or it's NATed behind. But we use these as replacements for virtual machines in many cases. We use it as a replacement for KVM. In cases where we're running Linux on Linux, we don't need KVM in many of those cases. LXD is confined using AppArmor, which is a mandatory access control system. It's confined using user namespaces so that LXD containers do not run as root. They run as an unprivileged user, meaning root inside of that container is not root outside of that container. In fact, UID 0 inside of the container maps to UID 10,001 outside of the container. So outside of the container, that user has no privileges, even though inside of it, it can apt-get install anything it wants. It can modify itself. It can remove its own file system. But if it escapes, it's an unprivileged user. So that's the discretionary access controls. Mandatory access controls are handled by AppArmor. This is what prevents any process, any rogue compromised process inside of a LXD container from assuming more privileges than it should have. It's confined. C groups are used to control the resources. This is how we prevent one container from taking over more of the system, more resources on the system than it should. Using C groups and LXD, we can limit the amount of CPU, the number of CPUs, the amount of time each container gets to use on that CPU as a percentage, the amount of disk space, the amount of network I/O, the amount of memory. So we can put the same virtual machine type limits on a machine container just like we can onto a machine. What you see here is kind of what a cluster of LXD might look like. It's important to understand that LXD has a REST API, and many different tools can talk directly to that REST API. The one that's maybe pertinent to the OpenStack crowd here is the Nova LXD driver. So Nova itself can provision LXD containers just like it can provision KVM or Xen virtual machines. And that's super powerful if you're really trying to optimize those resources. So mapping this back to developer velocity, Docker containers in many ways has helped developers go much faster in packaging an application, deploying that application as a unit, as a container unit. LXD helps developers really accelerate that machine provisioning. Every Ubuntu system by default has LXD on it. We started that in 1604, meaning every Ubuntu machine, be it a VM or a physical machine, is automatically able to run hundreds of other system containers just right out of the box. It's not activated, but it's on. It's installed out of the box. The last thing on this point is that these system containers can run various different operating systems inside of that user space. So it's quite common to have an Ubuntu host that's running a CentOS or a Fedora or a Debian or a SUSE user space. Now the one limitation is that it does have to be a Linux. We can't run Windows inside of a Linux container, but we can run any Linux user space, and we have a number of enterprise customers doing exactly that and using this as a much more efficient replacement for KVM. So the other tool in this space that is really important to us is something called Metal as a Service. Metal as a Service is a bare metal provisioning system that has gained tremendous popularity in the space where system administrators want to turn racks of physical machines and make those physical machines look and feel like a cloud, meaning provision that physical machine with one OS, destroy it, start over with another OS, do that repeatedly, use the same image that's being used in the public cloud on bare metal, dynamically reconfigure networks and storage. I'm actually a victim of the lack of network connectivity. I had intended to demo this machine, which is it's a little data center that fits in a rollerboard suitcase. So I flew in from Austin today, and this machine has basically 11 independent servers on it, and I can treat it just like a data center, and I can re-provision all 10 or 11 of those machines in minutes and destroy it and bring it back up. This is, again, about developer velocity, being able to treat physical hardware in that autonomous way that we've come to expect from the clouds and from container systems, okay? So MAS, Metal as a Service, is that tool. It's an open source tool that we lead at Canonical, but we've seen it deployed in many, many different places at this point by that developer-centric system administrator. Of course, this talk wouldn't be complete without discussing OpenStack. OpenStack obviously has opened up the data center in ways that I don't think any of us really truly expected or appreciated maybe a decade ago. So OpenStack now, having come all the way to the Q release, most of the way through the alphabet, has matured to a state where there are countless organizations that are completely aligned and dependent on virtualizing hardware using an open platform like OpenStack. Sab's talk was good, and I think the important point that I guess the prerequisite for that talk is the fact that you've got to have that OpenStack right already to deploy Kubernetes on top of it. So I think we're at a point now where it's just sort of expected that if you've got some hardware and you're aligned with sort of Linux and open source principles, there's going to be an OpenStack somewhere in the building. Now I will say that there's a varying degree of all-in on OpenStack. All of my labs everywhere throughout my entire corporation globally are going to be on OpenStacks, and that's the corporate alignment. That's one end of the spectrum. We've also seen another end of the spectrum where OpenStacks are they're compartmentalized. You know, one department has their OpenStack, another department has vSphere, maybe another department is doing something else. We see that entire range in the sort of that Ubuntu ecosystem and Ubuntu user space. We do quite a bit of work on this, but again, this maps to developer velocity in that organizations that have an OpenStack, developers can very easily spin up that infrastructure with OpenStack. So OpenStack's younger, cuter cousin is Kubernetes, of course, right? Kubernetes now, I would say, is right in the heart, sort of the center of gravity, currently the center of gravity in the container ecosystem. And you know, this entire talk could be just about Kubernetes and how it accelerates developer velocity. We could spend the entire hour talking about that. I'm curious, did anyone show up to this talk expecting this entire talk to be Kubernetes? Am I disappointing you by talking about a lot? Yes, a few people did. Are you disappointed that I didn't spend the entire hour on Kubernetes? Okay, good. There's lots of talks about Kubernetes. You can find them on, you can find ones that I've done and Kelsey Hightower and lots of people far smarter than me even on this. But there's no way we can't at least mention Kubernetes. So Kubernetes is all about container orchestration, right? All the infrastructure you need that is very specifically designed to run containers. Now there's been a lot of effort in the OpenStack world to retrofit OpenStack to work with containers, right? We've done a little bit of that with Nova LXD, which I would argue is a good fit because LXD is machine containers. They boot like a machine, they draw an IP address like a machine, they add storage and resources like a machine, but it's a container. There's quite a bit of work that's also been done in OpenStack to make OpenStack run Docker containers and run other containers. Personally, I don't think that's nearly as good of a fit as Kubernetes, which was designed very specifically for the cloud native, 12-factor to app, the real containerized workload. All those concepts that we started out talking about, that is exactly what Kubernetes was at Google long before anyone had ever said the word Kubernetes. This was Borg at Google. Now, to the benefit of everyone, I believe, Google open source Kubernetes, put it into a foundation, and now there's quite a bit of that center of gravity has now developed around Kubernetes. So we are required to call what we have in Ubuntu a distribution of Kubernetes, but that's like Linux Foundation trademarky sort of things. The canonical distribution of Kubernetes isn't actually a distribution of Kubernetes. It is just Kubernetes. It's open source Kubernetes compiled using the Ubuntu toolchain, but with no changes or enhancements or proprietary features or anything like that. What's super important and easy is that it's very easy to stand up a Kubernetes in Ubuntu. It's one command: conjure up Kubernetes and wait a little while, and you'll have a Kubernetes running. You can run it entirely on a local machine. I run it on my laptop all the time when I need to do some local Kubernetes development. You can conjure up Kubernetes and point that Kubernetes at MAS, that REST API, and it can put that Kubernetes across those 10 machines or 100 machines, your entire infrastructure. You can conjure up Kubernetes and point it at an OpenStack. If you give it your OpenStack credentials and key and the login and IP address, conjure up Kubernetes will deploy a Kubernetes to an OpenStack. You can conjure up Kubernetes against vSphere. Kubernetes knows how, or conjure up knows how to talk to vSphere and provision a bunch of VMware machines to run a Kubernetes. You can point it to your Amazon, your Azure, your Google infrastructure and spin up machines. Now, that's how you host your own Kubernetes if you're in the business of hosting a Kubernetes. But as we'll see in the case studies, there's lots of hosted Kubernetes services as well. And that's back to the fully managed, right? Someone's got to manage it. Unless your job is to manage a Kubernetes, you want someone else to manage your Kubernetes. I promise you that. What you get out of Kubernetes, I think the first talk, the lightning talk, showed quite a bit of that. And the concepts that I mentioned all map directly to Kubernetes itself. Lisa wanted to talk about edge computing, and so that is where we are here. So I'm personally very excited about edge computing, sometimes called Internet of Things, but that's not really what I'm interested in. I mean, I am. I've got lots of things, and I'm interested in that. I'm much more interested, though, in the industrial side of it, the smart computing that is being done in what are truly edge applications, right? So the drones and robots and the stuff that makes the headlines and people buy on Black Friday is one type of IoT. The IoT, though, that is really changing the way we live is the edge cloud case. It's the racks of computers that you never see that's making all of our lives quite smart. And that's the smart cities initiatives. That's revolutionizing the way we think about when we talk about transportation, retail, telco, energy. An edge cloud is very typically, it looks a lot like this actually. It's a small rack of machines, sometimes a half rack of servers. Sometimes it's a half rack in a full rack where the half rack is one vendor and the other half of the rack is another vendor. If you've ever been inside of the little hut under a cell phone tower, there's usually 3 or 4 edge clouds under that cell phone tower. AT&T has one, Verizon has one, Sprint has one, T-Mobile has one. There's 4 of them. And it's actually a cage with 4 locks on it, and each cage is a different vendor, and they're all sucking power off of the same grid. And they rent cables from one another that go back to the home office. But there has to be basically a small cloud under every cell tower by the time 5G rolls out in 2 or 3 years. Because so much computing is going to happen when you have hundreds of megabits streaming to every single phone, right? You need caching on the edge, you need transcoding on the edge, you need compression on the edge, you need encryption on the edge. There's quite a bit of computing that is required to do what we're all going to see on our phones in 2 or 3 years. We're doing a bit of work around we at Canonical, we're doing a bit of work around the Tokyo Olympics, which will really be one of the first places in the world that showcases the true power of 5G, and that's merely 2.5 years away. But it's coming like a rocket ship. The other place I could spend another hour talking about this. I do spend hours talking about this. The other place that I'm super interested in from an edge perspective is in the automotive space, the transportation space. That's cars. That's sort of the Black Friday equivalent of this, right? That's the smart car with the autonomous driving. But that's the thing that we all get into every day. You've also got to think about shipping, literally ships. So now back to nautical, right? We're talking tankers and ships that are moving goods across the world. Every single one of those has a data center on that ship because a lot of compute happens on that ship that can't happen elsewhere, whether it's loading or inventory or carrying information sometimes. It's trains, it's planes, it's automobiles. Self-driving is one very tangible case that is becoming a part of all of our lives. And again, within the next 3 years, will be an important part of the whole 5G circle in that connected cars, autonomous vehicles need connections and need a lot of connection. A lot of decisions have to be made inside of that car. It can't ask the cloud, can I change lanes right now, right? But every time that car parks, either at home in your garage or maybe it goes to, parks at Whole Foods and there's a network there, it downloads new information, a new inference engine with improvements to the decisions that it's going to make. It's also going to upload data. It's also going to share data, and that needs to be done in a secure manner. This is a place where developers writing applications are absolutely writing applications that are containerized and cloud native from the start, okay? This is a space that I'm passionate about because we see lots of Ubuntu running in those embedded devices, in those smart printers and cars and planes and trains and automobiles, the smart screen displays and stuff. But every one of those connected devices has to connect to something. And what do they connect to? They connect to a cloud. And it might be a public cloud, it might be a private cloud, it might be an OpenStack or a Kubernetes or something else. But what we find is that a lot of those devices that are running Ubuntu at the edge are connecting to instances of Ubuntu in the cloud somewhere. And that integration, the developers writing those applications on both of those ends are looking for that developer velocity. So I've already kind of talked to this slide as well because it's hard to not talk about the edge without talking about the back-end infrastructure, right? But back-end infrastructure is absolutely part of every edge device, right? A connected device isn't a connected device unless it's connecting to something. And what it might be connecting to is an application running in the cloud. So Lyft and Uber and Airbnb, these guys are all AWS, right? And that's their back-end infrastructure. But for every one of those you'll see another data center that springs up, a Facebook or something that runs their own physical data center. Either way, it's someone's cloud. And the connected devices, your Facebook endpoints are talking to that, and they have to have that to be useful. Okay, how are we doing on time? 10 minutes?
Yeah, we'll save some for Q&A.
Okay. Man, I saved the best for the end. Okay, case studies. I'll go through these pretty quickly. First of all, we see Ubuntu everywhere. I've selected a handful of case studies that focus on very specifically containers. But this is, take pictures, send this one around. This is a good one. We see Ubuntu everywhere. I mean, name a large-scale Silicon Valley type startup that started in the last 5 years. You know, the Ubers and Airbnbs and Instagrams. You know, these guys were Ubuntu from day one, and we do quite a bit of work to try to make sure that what they're doing is as efficient as possible in the cloud. Now, I've picked a handful of container use cases. So I'll talk to this one, Heroku. Heroku's a great story. This is a cloud native company, right? They are 100% Amazon Web Services. Everything that they do, every instance of Heroku that's ever run has been run inside of an LXC container running on an Ubuntu host inside of Amazon Web Services since 2010. That's a classic container use case. Now, these were machine containers, and these were containers long before we were talking about Docker containers. But for the most part here, we're really talking about cloud native development. In fact, 12-factor development. Some of the guys at Heroku created 12factor.net. I started here because this is one of the first organizations that I think about when I think about someone who really thinks about developers and what it takes for a developer to be successful. So everything that I mentioned, those 5 things, I could easily apply to Heroku. A developer who writes a Heroku app, they don't care what's running underneath it. They push some code and it's automatically staged and then running inside of Heroku. So Heroku it's software as a service, right? You use the Heroku service, but if you wanted to, instead, you want it to use, that was not the slide I expected. Yeah, this one. If you wanted to run that sort of platform as a service on-prem, if you needed your own copy of something like a Heroku, Pivotal and Cloud Foundry has been around for quite some time, creating a very similar experience, right? So about 90% of Pivotal's commercial deployments, and there is Cloud Foundry, open source Cloud Foundry, I don't know the numbers there, but Pivotal Cloud Foundry, 9 out of 10 Pivotal Cloud Foundries are running on Ubuntu, and Pivotal also uses LXC containers. So these are containers long before containers were cool, running applications, containerized, start, stop, destroy, live migrate, snapshot, clone, but just a classic container hosting platform that developers gravitate to. Developers, especially in certain verticals like financial services or something like that. This one is a different approach, but also quite popular in the financial services space. Hyperledger. It's another open source project. This one led by IBM. Hyperledger is it's sort of blockchain for grown-ups, or blockchain for business, right? So you can do smart contracts. There's quite a bit of interesting provenance of data that Hyperledger is able to deliver. Hyperledger runs on many different platforms, but it's quite well optimized for the IBM mainframe. So that's an IBM Linux 1 mainframe. Most of the Hyperledger that's deployed today is running inside of Docker containers on Ubuntu in mainframes. So that is very much a containerized workload using some of the oldest and most classic hardware on the planet. You know, we're talking 40-year-old technology baked into IBM mainframes here. So the Google Cloud Platform launched a hosted Kubernetes service. So I mentioned fully managed, and that's important. One way of getting full management of your infrastructure is using one of the public clouds and their fully managed services. So Google's Kubernetes engine is Google's hosted version of Kubernetes. You don't have to worry about spinning up the Kubernetes. You can spin up Kubernetes if you want, but if you want someone else to do that for you, Google offers that as a service, which is the Google Kubernetes engine. The worker nodes in Kubernetes are the nodes that actually run those containers. So we've worked with Google to launch this was a sort of customer feedback from Google. So Google has a couple of different worker nodes, one of which is their container OS. But Google came to us in the early part of this year and said, but our customers are finding that they are running their Docker containers on Ubuntu locally on developer laptops and stuff, and they're finding some incompatibility with running that inside of our hosted service. Can you help us optimize an image, a kernel and an OS image to run the worker images for Kubernetes? That makes the movement of workloads from on-prem or on a developer's laptop to work well inside of Google. So we launched this in September. Specially tailored kernel, optimized kernel, and optimized image for running Kubernetes workloads, pods essentially, inside of GKE, okay? Microsoft has a similar service, the Microsoft Azure Container Service, which is a hosted version of Kubernetes for that sort of Microsoft enterprise consumer, that customer. The Azure Container Service, the Kubernetes service, is actually based on Ubuntu. It started with Ubuntu from day one, whereas as Google started with Container OS and moved some of those workers to Ubuntu, the Azure Container Service is running Ubuntu as the base operating system. An example in the telco space is the Verizon telematics project. So back to the sort of the smart vehicles, the connected vehicles. Verizon has a suite of products for fleets of industrial vehicles. It's called Verizon Telematics. This is a project that involves Dell EMC hardware, Ubuntu as an OS, and Docker as the container system. And it's something that we partnered with Dell EMC, Docker Inc., and Canonical, and we continue to work with Verizon on the telematics project. And I think this is the last of the case studies I have here, and this is one of my favorites, is the Nvidia DG X1. The DG X1 is basically a supercomputer in a box, capable of running AI workloads shipped straight from the factory. So this is I think it's about a 4U or 6U system, rack-mountable system, packed with GPUs, a ton of CPU memory, and as many GPUs as will fit in that box. It's shipped preloaded with an optimized version of Ubuntu and Docker on that system, and a bunch of AI apps already packaged. So TensorFlow and Cafe4J and a number of other apps that if you're writing AI applications that you need and you want to run optimized for GPUs. And so that's the Nvidia DG X1. That slide's out of place, but I'll talk to it anyway. And this is the last slide. So actually, I'll skip this. We're going to go straight to questions. And I'm happy to come back to this one if we get to it.
Okay, so now questions. Okay.
Thanks. Just quickly, what's your philosophical thought about the long-term role of Nova in a world where containers become more and more part of the mix? Does Nova change? Does it become something other than VM dispenser? Does it play some of the role in infrastructure primitive for compute? What's your thought there?
Yeah, it's a good question. I'll repeat it just in case online didn't hear that. The question is, what's my long-term thoughts on Nova, especially in light of containers? I think Nova holds an extremely important part. I mean, there's really three facets to all the concept of cloud. There's compute, there's storage, and there's network, and the dynamic provisioning and allocation of each of those. Nova obviously handles the dynamic provisioning of the compute, the CPU memory portion of that. There's network and there's disk that comes in through other projects. It doesn't matter how well containers do, there will always be a place for virtual machines. We need virtual machines when we need to virtualize non-Linux OSs. So there are Windows workloads that need to run. There are BSD workloads that need to run. There are other operating systems that haven't been created or invented that need to run somewhere. And for those, full virtualization plays a very important role. That doesn't go away. There are a lot of things, as I've said before, that can move from full virtualization into containers, be it machine containers, or in some cases with a bit of application rewriting and re-architecting into a process or application container format. Nova is quite extensible. I've touched that code myself in the past. I've seen the Nova LXD driver. It's super simple, clean Python code. The fact that Nova is pluggable is part of the beauty of open source, and beauty of OpenStack is how pluggable it is. My comments earlier about OpenStack, not necessarily, this is a personal comment, but I think OpenStack is awesome infrastructure as a service. I think Kubernetes does a much better job of handling the container orchestration than OpenStack necessarily ever will be.
Another question.
Hi, thanks. That was a nice, interesting talk with respect to the history. So there are a lot of container OSs right now. Canonical has, you mentioned how you tweaked for Google. So there's CoreOS, which is having its own personality and its own perspective of how the container OS should be.
Sure.
The container Linux, and then Google now has a new for the GKE has a different OS. They moved away from the Debian, I think. How do you perceive those perspectives? Wanted to know your opinion on what kind of, in the containers world, how would you look at this container OS as? Do you think immutable container OSs is a good concept? How would you do it?
So the question is generally about container optimized operating systems and just how I see that. Well, I'm a distro guy. I've been working in and around Linux for almost 20 years. I started at IBM. I spent a year working for IBM, but on site at Red Hat. And I've been with Canonical working on Ubuntu for almost a decade. Making an OS is just, it's fun, man. You put five geeks in a room for a couple of days and they'll make a Linux distribution. It's sort of inevitable. And it can be a lot of fun. Taking that to the next level, to something that is production ready and ready for the enterprise, ready for regulated environments, ready for environments that have no tolerance for faults, zero fault tolerance, is a whole different world. It's a whole different scenario. So we do have basically two flavors of Ubuntu. We have traditional Ubuntu, which if you've ever used an Ubuntu system, desktop or server, and you've apt-get installed anything, that's what we call our traditional Ubuntu, or just Ubuntu. We also have another version of Ubuntu which is optimized for embedded environments called Ubuntu Core. Ubuntu Core, much like CoreOS, much like other operating systems sort of in that immutable infrastructure, Ubuntu Core works very much like that. We do work with a number of hardware manufacturers that are putting Ubuntu Core on devices, and they like it because the OS itself is as read-only as any firmware you've ever touched, a DDWRT or Android or anything like that. When you get to the point that you're ready to ship 1 million devices, Ubuntu Core is a great way to do that. Applications can run as containers, they can run as Docker containers, they can run as LXD machine containers, they can run directly as Snap application containers, which is a whole other container format I didn't even talk about here today. What I'll tell you is that the first time you sit down and you use an Ubuntu Core system, it will feel very unfamiliar. It is Linux. There's an etc and a var and a user and a /temp and home and those sorts of things, but it's as unfamiliar as sitting down and trying to do the usual Linuxy things on an Android system or on a DDWRT system. That's been a very similar experience that I've had when I've done some competitive analysis and investigation around CoreOS, Project Atomic, and other things. It's a whole different world. It's a whole different mindset. We do have a dog in that fight, which is Ubuntu Core, but Ubuntu itself isn't going anywhere, and there are plenty of devices that might run any one of those other OSs that are still running Ubuntu and will continue running traditional Ubuntu. I would say that in closing there, containers are a first-class citizen and have always been a first-class citizen on every form of Ubuntu we've ever put out, from desktop to server to cloud to virtual machines to other containers. Containers can host containers, and be that the read-only container OS or the traditional Ubuntu.
Last formal question from Rick.
I was fascinated by your discussion of LXDs early on, but it seemed like you were saying that they're not virtual machines, but everything you said seemed like they were virtual machines. Yep. It seems totally semantic. What is the distinction between LXDs and virtual machines, very specific and technically? Yeah, and I also want to add one more thing. Managing container hosts, to me, is a completely different technology than managing containers, and that's when we use tools like OpenStack is to manage the hosts. Yep.
Yeah, it's a good question. So the first question is about LXD. I talked about them like they're virtual machines, but they're containers, but they sound like virtual machines, but they're containers. That's exactly right. So, we're sitting here at VMware and we can talk about type 1 hypervisors, right? We can talk about type 2 hypervisors. And those were the two hypervisors that were defined in the seminal Watson paper from IBM in the 1970s, right? LXD is kind of a type 3 hypervisor. It has all of the semantics of a hypervisor. You start, you stop, you clone, you migrate, you back up, you snapshot. What happens inside of that container is an operating system boots. System D starts, it forks off a bunch of processes. Those processes then manage other processes and fork other processes. And other than there just being a kernel shared with the host, otherwise it behaves exactly like a virtual machine. I'm happy to run a demo here if you'd like to see what that looks like. And I'll keep the screen up. Some people I'm sure have other commitments to get to, but I'd love to show off a little bit of LXD here. It is a bit of a mind bender in that it's a container, but we treat it like a virtual machine. What we love about it and what customers love about it is that virtual machine applications can easily and trivially lift and shift into a LXD container, which is a little bit unlike Docker. And I put that, the we love Docker and Docker loves us slide up with complete sincerity. We genuinely love Docker. We do a lot of good work around Docker. One of the things that Docker isn't great at is the lift and shift application. Let's just take this thing that's been running on Wall Street for 20 years and put it in a Docker container, and now we're containerized. That doesn't typically work because a typical application, a Linux application, expects there to be log rotation, a journal running. Your management system expects SSH to be there with SSH keys so that Puppet can get in and do its thing. All of that takes a bit of re-architecting from an application perspective to work in a Docker world. And guess what? It takes a lot of re-architecting to make it work in a Kubernetes world, okay? That same application that just runs inside of a VM also just runs inside of a LXD container. And if you want to orchestrate that, then you use OpenStack, just as you said, to manage those machines, manage that infrastructure. And the lift and shift is absolutely trivial. I mean, absolutely trivial. And you get the advantages of containerization on the route to the route to the full Dockerization of your infrastructure for your new applications. It's great. Thank you.
Good stuff. Good stuff. Everybody, thank you so much. Thank you for all the out-of-town guests. Robert came from Tennessee. If you couldn't tell by Dustin's boots, he came from Texas and brought his own cloud. Feel free to come up and take photos. The cloud is not shy. It will be ready for its close-up as soon as this is done. And I think we've commissioned Dustin to stick around for a few more minutes. Commissioned. Yeah, right? We paid you to stay around for at least 10 more minutes?
Absolutely. Paid me in pizza and beer.
Paid you in pizza and beer. I know. Thank you once again to VMware Code for doing that. Don't forget to sign up so that they can get paid for the pizza and beer. And remember, December 13th, we'll be at Juniper. Randy Bias will be talking. Robert Starmer will be asking him the very hard questions at the end. So I might get the night off. Hey, yay. And thank you, Ron, for also filming this. And thank you, VMware, for live streaming it, our biggest live stream ever. I'm so excited about that. Thanks, everyone. I'm Lisa, and I'll see you guys on the 13th. Bye.